My name is Tanmay, and I'm presenting my PhD thesis defense titled Learning and Translating Temporal Abstractions of Behavior Across Humans and Robots. I'd like to get started by describing something that I think is quite remarkable. So consider an amateur cook on the right, learning to cook a new dish by watching a professional chef cook this dish on YouTube on the left. Now, people are really good at this. We can come up with incredible results despite operating with different equipment, with different ingredients, in different kitchens, and in entirely different environments. And what this sort of points towards is how good humans are at learning to solve tasks from demonstrations of other people solving these tasks. But it's not just demonstrations that we're good at learning from. We're also good at learning to solve tasks from instructions, from recipes, and other diverse sources of information. And in this thesis, I believe that there's two abilities that enable humans to do so. The first of these abilities is that people are able to reason over temporal abstractions of behaviors that are needed to solve these tasks, as well as the effects that these behaviors have on their environments. So what do I mean by temporal abstraction of behavior? When I say temporal abstraction of behavior, I mean that people reason over a pattern of motion or action that an agent executes over a period of time towards a consistent goal, rather than reasoning about the low-level actions at each and every time step during that behavior. And I'm going to use the phrases skill and behavior sort of interchangeably throughout this talk. Let's consider an example to look at what this ability means. Let's say I'm trying to pour water from a jug into a mug, as you can see here. Now, I don't really care about the angle that my wrist is at any given time step during this task, as long as I do this in a consistent manner over a period of time such that leads to the desired effect. That is, I abstract away these irrelevant details and instead focus on this temporal abstraction of behavior. In the cooking example, this looks something like this. There's a sequence of steps or behaviors or skills that a person will execute in order to cook this dish. And this might look something like cutting the meat or adding oil to a pan and putting meat in a pan and so forth. And people inherently reason over these behavioral abstractions of each of these steps. There's another ability that people have that enables them to imitate demonstrators so well. It's the ability to understand high-level strategies of a task in terms of temporal abstractions and find corresponding abstractions for themselves to execute. So let's go back to our cooking example to see what this looks like. You have a demonstrator who's executing some sequence of skills, and a person watching this and trying to learn from it is able to recognize this sequence of skills and find a corresponding set of skills for themselves to execute. So there's this notion of some kind of correspondences or mapping between the skills that a demonstrator executes and the skills that a learner executes. Now, these two abilities together offer us a shared perspective of the strategies that people use to solve these tasks, the skills and the effects that these skills have across both the demonstrators and learners, agents, and domains. Now let's consider a robot trying to cook you this dish by watching a professional chef cook this dish. How do we enable robots with these two abilities that humans have? That's the core question that my thesis has been trying to answer. More formally stated, the question that I've been trying to answer is how we can learn and translate temporal abstractions of behavior across humans and robots in an unsupervised manner. And I've tried to do this in a few different ways in my thesis. Specifically, I first looked at the question of acquiring and representing abstractions of behavior. And I will briefly present one work that does this and sets up an important piece of machinery that I use throughout my talk. I'll then also discuss how we can acquire representations of the effects of these behaviors on their environment. And then I will shift gears into talking about how you can translate these abstractions across humans and robots. And for this, I will briefly present one work that introduces this problem setting, and then go into more detail about another work that addresses this more comprehensively. Finally, I will end with some ideas on how you can take some of these concepts and apply them to this idea of translating human motion to art domains. With that, let's get into part one of the talk, which deals with acquiring and representing behaviors. The project that I'm very briefly going to present is titled Learning Robot Skills with Temporal Variational Inference. This was published at ICML 2020, and it forms an important backbone of most of the work in my thesis. This deals with the first half of ability one, that is, acquiring and representing temporal abstractions of behavior. Formally, we'd like to address the question of how robots can acquire and represent temporal abstractions of behavior. To go back to our cooking example, just as a reminder, this looks something like this. I'd like to be able to learn these behavioral abstractions that capture the sequence of behaviors or skills that an agent executes while demonstrating a task. How we went about this in this particular project was assuming that we had access to a robot demonstration data set of a robot performing a variety of different tasks, from which we assume we can extract a robot trajectory. This robot trajectory gets encoded into a behavioral abstraction depicted by this latent vector ZR here via some encoder QR. Now, this behavioral abstraction captures the pattern of motion or action executed by the agent during the course of the trajectory. And in reality, this one trajectory could be encoded as a sequence of such behavioral abstractions. And each behavioral abstraction forms part of a larger learned space of skills, where each point in the space represents a unique skill, and different parts of the skill space represent different kinds of skills. So for example, these orange points might represent something like twisting open a bottle, and the purple points might represent something like pouring from the bottle. And you can decode any point in this skill space via a robot policy to roll out a trajectory that you can execute on your robot. And in order to train this pipeline, we introduced a temporal variational inference framework that is able to learn the skill space in an unsupervised manner from these demonstrations. Here are some of the skills that we were able to learn using this framework. So you see things like stirring and pouring and box opening and so forth. But more interestingly, the thing that I'd like you to remember from this part of the talk is that we were able to come up with these ideas of a learned skill space, where each point in each of these skill spaces represents a unique skill that the robot can execute. And we were able to learn these skill spaces across a variety of different domains in an unsupervised manner. So without access to any supervision over the number of skills we were trying to learn, temporal segmentation information of these skills, semantic segmentation information. Yeah, and this is a really cool idea of being able to learn a skill space. So the takeaway from this part of the talk is that we were able to see how we can address this ability one of acquiring and representing abstractions of behaviors by viewing it from a representational learning perspective. And this representational learning perspective afforded us this notion of these learned skill spaces. With that said, let's jump into part 2 of the talk, which shifts gears into addressing unsupervised translation of skills. The project that I'm again going to briefly present here is titled Translating Robot Skills, Learning Unsupervised Skill Correspondences Across Humans and Robots. And this was published at ICML 2022. Now, this shifts gears from into addressing how you can translate these temporal abstractions of behavior across humans and robots. Formally, the question that we were trying to answer was how robots can learn unsupervised correspondences between their own skills as well as skills of a demonstrator, whether that demonstrator is a human or a robot with a different embodiment. The key here being that you'd like to do this in an unsupervised fashion, because acquiring skill-level correspondence supervision is an expensive form of supervision that we want to stay away from. So let's go back to our cooking example. We saw in part 1 of the talk how you can acquire these behavioral abstractions that represent motions or behaviors in each domain. And we saw how we could do this in any arbitrary domain, so both the source and the target domains. In this part of the talk, we're going to address how we can learn correspondences between these two sets of behaviors or skills. So the problem setting that we're going to consider is that I'm going to assume that I have access to demonstration data of a demonstrator agent that can be a human, as depicted here, or it could be another robot, and that we have some skill representation learning technique that affords us a learned space of skills. In practice, this skill representation learning technique is the temporal variational inference approach that we introduced in part 1 of the talk. In principle, I think you could use other skill representation methods, but for now, we're using the temporal variational inference approach. So we have this set up in our source domain of the human demonstrator. And we're going to assume that we have a very similar setup in the target domain of the learner robot. So you have demonstration data of a robot performing a variety of different tasks and a corresponding skill space on the robot domain. We're going to assume that there is no parallel data or no paired demonstrations between these two domains, but that there is overlap in the tasks that they each try to solve. And what we'd like to learn are these notions of correspondences across both of these skill spaces. So for example, that any one point in this source skill space corresponds with this other point in the target skill space. In other words, we'd like to learn a translation between these two spaces, or some kind of mapping between them. Now, if you take a second to look at this problem setting, there's unlabeled, unsegmented demonstration data in your source domain and your target domain, and some learned representation in your source and target domains that you're trying to learn a translation function across. This is actually very reminiscent of the unsupervised machine translation problem, where you have unlabeled, unsegmented corpora of text in your source and target languages, and you're trying to translate across some word or phrase representation. So we make this insight that learning skill correspondences is equivalent to the unsupervised machine translation problem. And this is really neat because it affords us the ability to use all of the machinery that unsupervised machine translation uses to solve our skill correspondence problem. So we do this, and we start off with a source domain skill space and a target domain skill space. You can then initialize some translation model, retrieve a translated skill space. The question then being how you actually learn this translation model. You can do a bunch of different things here. You could do things like domain adversarial training, or back translation, or cycle GAN, or state imitation. There's many other approaches that unsupervised machine translation has used to solve this. And a lot of them boil down to this idea of distribution matching. So we run with this idea and instantiate our version of distribution matching as sequences of skills that each agent execute should belong to similar distributions, irrespective of the embodiment of that agent. The idea being, whether I have a human or a robot try to make me a cup of coffee, they're both broadly going to follow this sequence of opening up a cupboard, reaching for a cup, grabbing the cup, and so forth. And we operationalize this insight by first estimating the distributions of sequences of skills in the source and target domain, and then coming up with an objective that tries to match these distributions. And without getting into too much detail of how this happens, this approach was able to give us these coarse semantic level correspondences across multiple domains. So let's start out with this pushing skill of a human pushing an object with its right hand. We were able to translate this to a Baxter's left and right hands, as well as a Sawyer and a Franca robot, all without any correspondence information between any pair of these two domains. Here are some visualizations of other skills that we were able to translate. So you were able to translate this. I'm depicting this for the human and the Baxter pair, but you can translate between any arbitrary pair of agents. And this is a really cool result, considering you don't have any supervision between any pair of domains. That said, there are some limitations to this approach, and it's important to be aware of them. The first of these limitations is that this approach is unaware of the objects in the environment and the environments in general. The second is that this approach of matching skill sequence distributions across source and target domains only affords us coarse semantic correspondences. It doesn't afford us finer semantic correspondences. And that's something to remember. These limitations aside, this work sort of looked at how we can address the problem of translating temporal abstractions of behavior across humans and robots, and view this from an unsupervised translation perspective. And this unsupervised translation perspective affords us the ability to do this in an unsupervised way. I'm going to pause here for a second, and then we can jump into part 3 of the talk. So one of the things that you may have observed in the results that I showed you so far is that they're largely, especially in the translation work, there's no objects in the scene that the robot was interacting with. And this is a pretty big limitation. So in this part of the talk, we're going to shift gears into translating environment-aware task strategies instead. The project that I'm going to present in a lot more detail is titled Transact, Translating Agent-Environment Interactions Across Humans and Robots. And this was recently accepted at IROS 2024 as an oral. And it deals with both ability one of addressing, acquiring and representing abstractions of behaviors and their effects, as well as how you can translate those abstractions across humans and robots. So let's go back to our cooking example. In part 1 of the talk, we saw how we could acquire these behavioral abstractions that represent patterns of motion of the agent themselves. But in reality, these agents aren't executing these skills or behaviors in isolation. There's also a notion of the effects that each of these behaviors have on their environments. And just as these behavioral abstractions capture the patterns of motion that the agent executes, we can also build environmental abstractions that capture the patterns of motion observed in the environment during the execution of a particular skill. You can then also imagine combining these behavioral and environmental abstractions to form what we call interaction abstractions that essentially capture both the motion of the agent over the course of a particular chunk of the trajectory, as well as the motion observed in the environment as a result. These interaction abstractions are really useful for modeling certain types of tasks where the trajectory that the object undergoes is important. So for example, if I'm pouring from a jug into a cup, it's really important that the object undergoes this trajectory of progressively tilting more and more over a period of time. And it's not just important what the goal state of the object is. So these interaction abstractions let you capture things like that, where there's a trajectory of the object that needs to happen in the skill, and capture the interaction between the robot's motion and that environment motion. Another example of this kind of task is something like unscrewing a bottle cap or screwing in a light bulb, where there's a constrained motion that you need to model. And once we're able to learn these interaction abstractions on any given domain, we'd also like to see how we can translate them across humans and robot domains. And again, this affords us a shared perspective of the skills as well as their effects across these agents and domains. And this would in turn allow learner agents to adopt a demonstrator's task strategy to similar effects. The questions that we were trying to address in this part of the talk were first, how robots can acquire temporal abstractions of interactions. So how they can jointly model both their own behaviors as well as the changes observed in the environment as a result of that. And once we have such abstractions, how we can then translate these abstractions of interactions from humans to robots with minimal supervision. To scope the problem a little bit, I'm going to instantiate environments as two free or articulated objects in a tabletop setting. Agent state is represented as joint angles. Object state is represented as 60 position and orientation of the object. And you can later consider relaxing this to multiple objects, different state representations, and deformable inputs, and so forth. And I'm happy to talk about how I think we can do that after the talk. So the problem setting that we consider is pretty similar to before. We assume that we have a demonstration data set of a robot performing a variety of different tasks. For this project, we collected a real-world robot data set. Shout out to Chaitanya and Elliot, who helped set this up, where I'm sort of kinesthetically demonstrating a task on a lead robot and have this follower robot copy the motions of the lead robot. And then we assume that we have some interaction representation learning technique that gives us a learned space of interactions. Now, this learned space of interactions is analogous to the skill spaces that we saw before, except that they also capture the motion observed in the environment during the execution of a given skill. So for example, this top left corner of this space might be something like opening up a drawer. The top right corner might be something like opening up a box. And then there's other interactions in there, such as pouring from a cup, and then stirring a cup with a spoon, and so forth. We also assume that we have an identical problem setting on the human domain of the demonstrator. So there's a human demonstration data set of the human performing a variety of different tasks. There's an interaction representation learning technique that gives us a corresponding interaction space on the human domain. The transfer setting is pretty similar to before. We have a source domain and a target domain, and we're trying to learn some kind of translation function across these two domains. I want to take a second to talk about some of the assumptions that I'm making in this problem. I'm going to assume that I have object state information given to me by tracking some fiducials. I'm also going to assume that I require demonstrations in both my source and target domains. There is still no parallel data or no paired demonstrations across these domains. And we assume access to task level labels, but nothing, no other supervision besides that. So no temporal segmentation information of the trajectories, no number of interactions that we're trying to model, no semantic segmentation information, and no dense correspondences between the two domains. And finally, we also assume that the humans and the robots are in the same environment. This sort of implies that there are similar distributions of object state and viewpoint and physics properties and so forth. And this is somewhat of a restrictive assumption, but it's a good starting point. So that said, how do we go about this translation problem? In part 2 of the talk, we saw that you could do this via a variety of unsupervised machine translation approaches. But one of the issues that we saw from that is that they were environment unaware. In this part of the talk, we're going to go about this slightly differently. We're going to translate human interactions to their robot counterparts by retrieving robot interaction representations that have similar environmental effects. The caveat being they're in the same environment, as I mentioned. But I want to take a second to talk about this idea of matching environmental effects, particularly when there's a large morphology gap between the demonstrator agent and the learner agent, as is the case here between this dexterous human hand and a two-fingered robot gripper. Imitating the actions or the states of the demonstrator agent is not necessarily the best thing to do. Instead, what you care about is that the skills that they each execute lead to similar effects in the environment. So if I have a human pick up a cup or pick up a bottle and pour from the bottle, I'd like my robot to also pick up the bottle and pour from it. Yeah, that said, I'm going to briefly describe the interaction representation work, or how we go about learning the representation of interactions. And then I'll talk about how we can go about translating them across domains. So let's start with how we can go about learning this representation of interactions. Now, we'd like to inform our choice of how we go about learning this representation based off of the fact that we're going to transfer this by retrieving interactions across these two domains. So what properties would I like my representation to have in order to facilitate easy retrieval downstream? Well, one of the first properties I'd like it to have is that I'd like the representation to be factored with respect to the agent and the environment. I'd like my representation to be robust with respect to perturbations in the input and smooth in its representation space. I'd like the representation to be contrastive with respect to the different interactions that it encounters. And finally, I'd like my representation to be accurate or high fidelity with respect to the underlying interactions. Let's discuss this idea of factored agent environment representations in a little bit more detail. As before, we're going to assume that we have access to a demonstration data set of the robot performing a variety of different tasks, and that we can extract some robot trajectory as well as an object trajectory from this demonstration data set. This object trajectory or environment trajectory just consists of concatenated object trajectories over time. And we're going to treat each of these two trajectories as sort of separate streams of information. In particular, we're going to encode them into a respective behavioral abstraction, ZR, and an environmental abstraction, ZE, via the respective encoders QR and QE. And these behavioral abstractions capture the motion of the agent in its environment, and the environmental abstractions capture the pattern of motion observed in the environment itself during the execution of a particular skill. Together, you can consider concatenating these two into something like an interaction abstraction, which jointly represents both the pattern of motion executed by the agent as well as the pattern of motion observed in the environment. And as before, each of these interaction abstractions forms part of a larger space of interactions. You can then take any one of these interaction abstractions, feed it through your policy, roll out your policy to retrieve a robot trajectory that you can execute, as well as the anticipated object trajectory that you expect to see. Yeah?
Can you say one more time, what's tau R and what's tau E?
Tau R is essentially a trajectory of the robot. So it is specifically represented as joint states over time of the robot alone. Tau E is the 60 position and orientation of each object concatenated with each other over time. Does that make sense? Perfect. OK. So this describes how we sort of went about factoring our representation. So this idea here that the interaction abstraction representation consists of these two components is what we're referring to when we say a factored representation. Now, I'd also like for my representation to be robust with respect to perturbations in the input and smooth in the encoding space. And this would facilitate downstream retrieval more easily. So let's say we have a trajectory, and this trajectory gets encoded into this little purple dot in my representation space. Were I to perturb the trajectory, the encoding of this trajectory would change. Ideally, I'd only like for my trajectory's encoding to change by a little bit. What this does is it pushes similar trajectories into similar parts of the representation space, thereby facilitating accurate retrieval downstream. We can actually encourage this property in the representation by measuring the input deviation, measuring the output deviation in the representation, and then discouraging the encoder Q from having a large magnitude of its Jacobian. And we do this in the form of a Jacobian regularization loss. This Jacobian regularization loss forms an auxiliary component of our overall objective. We'd also like for our representations to be contrastive with respect to the different kinds of interactions that they encounter. Let's say we have a representation space where there's lifting interactions and pouring interactions, represented in purple and green dots, respectively. Ideally, I'd like for my representation to have all of the lifting interactions close to each other and far away from the pouring interactions, because again, this would facilitate easy retrieval of a particular type of interaction. Now, contrastive learning provides us useful machinery to do this. We can measure the distance between positive pairs in the representation space and the distance between negative pairs in the representation space, and then come up with an objective that encourages this property. The question then being, well, what are my positive and negative pairs? We explored two ways of instantiating this. The first is, given that we have access to task labels, we explore this idea of task contrastive learning, where the representation is trained to be discriminative between interactions from different tasks and contractive between interactions from the same task. And we come up with an objective that encourages this. The second component that we explore is perhaps the more interesting one, where we explore this idea of being contrastive with respect to the effects that these trajectories have on their environment. In particular, we'd like the representation to be discriminative between trajectories that have dissimilar or different environmental effects, and contractive between interactions with similar environmental effects. And you can measure the environmental effects by doing things like taking a trajectory, or taking a pair of trajectories and comparing either the distance between them, or the dynamic time warping distance between them, or the distance between a proxy representation of them. And you can come up with another objective that encourages this property in the representation, and we combine both of these objectives into an auxiliary contrastive loss that forms another component of our objective. The third component of, that we'd like in our representation is that we'd like it to be accurate with respect to the underlying interactions. And I'm not going to go into this in as much detail, but essentially given a trajectory that gets encoded into a representation and decoded into a rolled out trajectory, there's a notion of this rollout trajectory being different from the original trajectory that you're trying to reconstruct. And in addition to a standard reconstruction loss that just minimizes the distance between the ground truth and the predicted trajectory, we'd also like for this representation, or the policy in particular, to be corrective with respect to the errors that it sees. And in order to do that, we introduce a cumulative state reconstruction loss that sort of forces the policy to be corrective with respect to errors in the prediction that it encounters. And this forms the final component of our objective, that is a cumulative state reconstruction loss. Overall, our objective looks something like this. We start out with a temporal variation inference objective that was used in part 1 of the talk to train our original skill space. We add in an auxiliary Jacobian regularization loss, an auxiliary contrastive loss, and an auxiliary cumulative state reconstruction loss. Together, these form the objective of transact our system. And this overall describes the, how we went about solving the learning representations of interactions in, let's say, the robot domain. Now let's talk about how you can translate these interactions from a human domain to a robot domain. So we're going to start off with the representation space that we learned in the robot domain. And we're going to consider a query demonstration on the human side of a human demonstrating a task that you now want the robot to imitate. So you have this query demonstration, and you have a trajectory that both the human and the robot, the human and the environment undergoes during this demonstration. And we extract the environment trajectory from this query demonstration. So tau e human here represents the trajectory of the objects in this query demonstration that represent the desired environmental trajectory that you'd like the robot to imitate. So in this case, it's something like picking up the cup, pouring the beads into the cup, into the box from the cup. Now you can take this tau e human, the trajectory of the environment in the human domain, and encode it into a desired environmental abstraction, ze human, via your encoder QE. Now here you can actually share the parameters of QE with the QE in the robot domain, because we assume that both of these demonstrations are in the same environment. Now what we'd like to do is we'd like to take this desired environmental abstraction ze human, and then find the nearest neighbor of this in the robot representation space of interactions. So what does this look like? Well, we take this desired environmental abstraction, and you take your learned space of interactions on the robot domain. And let's consider a particular point circled in red here. Now, this point in red consists of two components, a blue behavioral component and a green environmental component. And perhaps this red point has the environmental component of it most close to the desired environmental abstraction ZE human out of all of the points in the representation space. So we take the behavioral component of this point in red, and this forms the result of our nearest neighbor query. Now, this behavioral component ZR star essentially represents the robot skill that was used to construct the closest environmental effect to the desired environmental abstraction ZE human. Hopefully that makes sense. Yeah.
So you're only using the green part to do the nearest neighbor lookup, is that right?
Yeah. The idea being you only want to compare the environmental effects. You don't actually want to compare the agents themselves because they could be entirely different morphology. Yeah. Great. So we take this this result of our nearest neighbor query, the retrieved robot skill. We concatenate it with the desired environmental abstraction to form our transferred interaction. This transferred interaction should represent the pattern of motion that you'd like the robot to execute in order to achieve the desired environmental abstraction. And then you can feed this to the same robot policy as before, roll it out, retrieve a trajectory that the robot can execute. You also have a predicted object trajectory that you anticipate to see in the real world. You sort of discard that. And this is how we go about the transfer aspect of our approach. And overall, this forms our framework Transact of translating interaction abstractions across humans and robots. So what does Transact enable us to do? I think the key thing that Transact enables us to do is this idea of zero-shot transfer from human to robot task strategies when the humans and the robots are in the same domain. So let's look at a video example of this. I start off with a query demonstration of a human performing a task such as opening up a box, reaching for the cup, pouring some beads into the box, and so forth. Now, Transact is able to encode this demonstration into a sequence of retrieved interactions that you can then use to condition a policy and roll out your policy on the robot performing this same task. And we're able to retrieve a rollout for different initial and relative configurations of the objects and slightly different instances of the objects. And the robot isn't perfect at this. It's sort of messy when it's pouring beads in particular, but it's still able to copy the overall sequence of interactions that was observed, namely reach for the box, open up the box, reach for the cup, teleport the cup over the box, pour from the cup, place the cup back, and so forth. We were also able to do this for other tasks, such as pouring from this cup and then stirring the beads in this cup using this wooden stirrer. And you can see the robot is also able to do this, admittedly, while spilling a lot of the beads from the sort of narrower receptacle. And finally, we were able to do things like opening up a drawer and placing a cup inside this drawer for slightly different instances of the objects and relative configurations of the objects. And remember, the only labeling assumption that we had access to here was task-level labels and demonstration information, of course. Despite that, I think it's pretty cool that we're able to do this in this sort of zero-shot fashion when the robot hasn't actually seen this task in training. Another cool thing of this Transact framework is that we're able to learn these spaces of interactions that capture a diverse set of interactions. So you have things here such as the robot opening up a drawer. In the top right, you have the robot opening up a box in different stages on the left. Yeah, these are the box opening examples. There's some placing cups over there. And yeah, there's also pouring interactions over here, some stirring interactions over here, and so forth. We also did more quantitative evaluations of Transact to verify that it was doing what we thought it was. The first thing that we did was to evaluate how accurately Transact is able to represent the various interactions that it observes. So we did this for several real-world data sets that we ourselves collected, as well as several existing simulated data sets that are out there. And we compared this against a few baseline approaches that are intended to span both classical approaches as well as learned skill approaches. And what we were able to see is that Transact was able to learn more accurate representations of agent-environment interactions than the baseline approaches. The biggest difference that this has is that typically the skills that Transact executes are able to interact with the object as intended much more successfully than the corresponding baselines. We also did a study of the relative importance of the various components of Transact, again, for the real-world data sets, for several transfer settings, and across some of the simulated data sets that we saw before. And what we were able to learn from this is that the state reconstruction loss was really important for the accuracy of the interactions, but the other three components were really critical for transfer. So in particular, the Jacobian regularization, the factored approach, and the contrastive loss were critical for transfer, and without any of those components, the transfer performance significantly degraded. The other really cool thing that we were able to note is that the full Transact objective is able to translate trajectories that perform at a similar level to a model trained in the target domain demonstrations itself. And that's actually kind of cool. It says, even if I have an approach trained on my target domain, the reconstruction errors that we're able to achieve after translating in a zero-shot fashion is on par with that, which I think is pretty cool. So that describes our Transact framework. Now, these cool results aside, I think it's also important to discuss some of the limitations of this. In particular, I still require there to be demonstrations in the source and target domains. This is particularly expensive in the target domain, where it's hard to access demonstrations of the robot, such as maybe a dexterous hand or so forth. And I also require these demonstrations to be in the same domain right now, which I think is another pretty big limitation. These limitations aside, there are some important takeaways from this work. First, we saw how we can address this ability of acquiring and representing abstractions of behaviors and their effects, as well as how to translate these interaction abstractions across humans and robots. And we saw how we could do this by matching environmental effects across these two domains. And we saw that doing this afforded us this zero-shot transfer of task strategies from humans to robots, which I think is a really neat thing to have. I want to talk about how we applied some of these ideas to translating human motion to art domains. And the project that I'm going to talk about very briefly here is called Coach Frida, encouraging exercise in older adults via interactive robot artists. Quick shout out to some of my collaborators on this work, Peter and Vihan in my lab, also Roshni and Reina in CMU, Rian Preston in Oregon State, and Mega from Georgia Tech. And this project sort of shifts gears into looking at some of the ideas from parts 1 and 2 of the talk and applying them to the domain to the art domain. In particular, we were interested in seeing how we can build this interactive robot system to motivate an adult to exercise more by translating human motion to paint strokes. And this work is very much a work where we took our pipeline and applied it to a new application domain, and so it was a sort of system integration effort. So here's a video of me doing some exercises, and our system broadly looks at the quality of these exercises, and then provides this to Coach Frida, our interactive robot artist. And Coach Frida is able to paint a visual representation of how well this user performed their exercises. Now, we had a few different ways of doing this. One of the ways we did this was first estimating the joint angles, thanks to Roshni and Reina for this component of the work, and then estimating the quality of any given repetition of the exercise. And then we have Frida decide what it is going to draw, and then plan out and execute a lot of the strokes that it's going to draw. So on a finer level, it takes the set of exercises that I do, and maybe my first repetition gets mapped to a particular point in this representation space where I have a good lateral raise. I have great range of motion. And this gets mapped to the robot performing a green paint stroke over here. Now, maybe my next repetition isn't as good. It gets mapped to a different part of my latent space where I have too high of range of motion. And this gets mapped to a yellow paint stroke over here. And finally, by the end of the exercise, I'm tiring out a lot. My range of motion is really low. And this gets mapped to a red paint stroke over here. And put together, we're able to take a demonstration of a person performing their exercises and then map this over to to the robot painting an entire painting, that's a visual representation of how well their exercises were performed. And it sort of modulates what strokes it's using based on what exercises they're performing, as well as how well they're performing those exercises. And you get this really cool color-coded chart of how well you did your exercises on a given day, which I think is pretty neat. And I'll just let it finish up. Yeah, and another thing we were able to do from this work was we ran a sort of restricted version of this demo at the Berkeley Rehabilitation Hospital. It didn't have some of the same perceptual components as I mentioned before, but it was still really cool getting feedback from the hospital staff and the patients there about our system and how we can improve it. That said, I'd like to address some perspectives on learning and translating temporal abstractions of behavior. We saw how we can address ability 1 of acquiring and representing abstractions of behaviors and their effects. And we saw how we can do this from viewing this as a representation learning problem. We then shifted gears into talking about translating temporal abstractions across humans and robots, and how we can view this problem from an unsupervised translation perspective. Finally, we explored this idea of approaching this human-to-robot skill transfer by matching environmental effects across domains. And I think the biggest takeaway from my talk, if there's one thing you'd want to take away from this, is that this idea of unsupervised translation of temporal abstractions is really a broad paradigm that you can view many different problems within. And here are some problems that I think you can actually view within this framework. So some future directions that I think are enabled by my work and would be prudent to follow are broadly along the themes of translating arbitrary temporal abstractions of behaviors. So I've broken this down into the short horizon, where there's alternate application domains, the medium horizon, where I'm talking about some new machinery, and finally the long horizon, where I'm talking about unsupervised translation as a paradigm. So the two complementary application domains that I think would be really interesting to follow up on are translating from dexterous human hand behavior to dexterous robot skills. This is something I've sort of slightly explored with Al in the back there, but we didn't have much success with in the past. But I think it could be really impactful and goes hand in hand with some of the work that I've done on translating robot arm motion to human arm motion. Sorry, human arm motion to robot arm motion. Another area that I think would be really useful is translating from more abstract signals, such as EMG signals, to prosthetic and bionic hand control. And I think this could be a really cool way to make this technology both more accessible and design it more with accessibility in mind. But I think there's some new machinery that we would need to introduce to solve some of these problems. In particular, I think I need to move away from this idea of using demonstrations in the target domain towards using interaction data instead. This would enable us to transfer to domains where you don't have demonstration data, such as dexterous hands and so forth, and where it's just more expensive to collect that demonstration data. I think we can go about this by things like matching environmental effects, because matching environmental effects is a signal that you still have access to even when you're dealing with interaction data. And I also think we can do this by things like matching distributions of object state or distributions of contact if you have access to tactile feedback. Finally, I genuinely think of this idea of translation of temporal abstractions of behavior as a paradigm. I started my talk describing that humans are good at learning to solve tasks not only from demonstrations, but from instructions and recipes and other diverse sources of information. And I envision this being a framework where you can have a source domain that consists of demonstrations and natural language instructions and policy sketches and so forth, and come up with a multi-domain, multi-modal abstract representation that you're able to transfer from to a learned skill representation on your target robot. And I hope that this takes us towards the marvelous robot that's able to solve tasks, not just from demonstrations, but from instructions, recipes, and other sources of information. Thank you. With that, I'd like to thank some of the people who have made this possible, without whom I would not have been able to complete my PhD. So starting off with Jean, my advisor. Jean has given me an incredibly long leash during my PhD, and I am tremendously grateful for that. She's also been the most supportive and encouraging person throughout my PhD, for which I'm tremendously grateful and really appreciate how you've done this even when I've had sort of health constraints in my PhD. Dave, for having given me feedback both throughout my PhD as well as earlier in my master's that I've always appreciated. Shubham for having done the same, both during my PhD and at my time at Meta. And I've sort of tried to imbibe a lot of Shubham's research process. And Amy, who's given me feedback not just on my research and not just in terms of related works that would be relevant to check out and so forth, but also more general advice on my career. There's been more advisors along the way whom I'd like to thank. Abhinav during my time at Meta, Chris and Katharina during my master's, Stuart when he was my manager, and more collaborators along the way. There's also been a lot of institutional support that I've received, particularly from the RI. I'd like to shout out Suzanne and BJ for having done so much work on my behalf, both during my PhD and my master's, for the AI Caring Grant for having funded much of this work. The Big Lab in general, who've been really supportive and helpful of much of my work, and Meta, where I learned a lot of really cool things. Here's some cool pictures of people at my lab, and it's been a really fun time, both going on trips with them and also having them be my partners in crime and research. Here's some of my mentees whom I've learned a lot from, like practicing research with. Here's a quick shout out to some of the AI caring folks whom I've worked with in the past. I don't have photos of all of you, but it's been really interesting and fun to come up with a system integration project with you. And beyond my academic collaborators and colleagues, there's been a larger community whom I'd love to thank. My CMU in Pittsburgh community to start off with, who've made my PhD an enjoyable experience and a fulfilling life experience in general. Here's more photos of us, because I have a lot of them. My soccer friends, if you know me, soccer is an integral part of my life and my community, and I'm thankful for having then made my PhD fulfilling. Friends both far away, whom I've either visited or who've come to visit me. Friends who've largely shaped my interest in science. Ali for having been there for the past 2.5 years and supporting me in my PhD, and personally, Ali's family who've given me a home away from home. And of course, my extended family, who've always been nothing but encouraging and supportive of me pursuing my academic pursuits. My family, without whom none of this would have been possible. They've sacrificed so much and given me so much in order for me to be here. Here's more photos of my family. My sister, whom it's been great to be able to lean on emotionally and academically as well. And I want to take a quick second to remember my dad, who was incredibly proud of me when I came to CMU in 2014 for an internship, and who I'm sure would be incredibly proud for me to have returned for my master's and my PhD. And of course, my mom. Here's my mom trying to teach us about gravity with Hot Wheels cars on a Hot Wheel track. I have her to thank for much of my intellectual and academic curiosity. Here's some more photos of us roaming around. And a quick shout out to my parents, without whom none of this would have been possible. I'm incredibly grateful for their support and for having facilitated me in this journey. Thank you. With that, I'd like to stop and ask if you have questions. Yeah, thank you.